Okay, so now we're going to add another layer or another wrinkle to our ionic compound nomenclature. And we're going to now see the presence of a different type of ion called polyatomic ions. Okay, so up to this point, so previously we've seen monoatomic ions or monatomic ions. So things like magnesium or the oxide, O2 minus, or sodium, Na plus, etc. These were made up of a single atom that eventually became an ion. Polyatomic ions consist of combinations now of two or more atoms that have an overall charge on them. Okay, so there are several of these polyatomic ions that we're going to see. Um, we're going to treat them the same way as we would uh, our monoatomic ions, with one important exception. That is when we put it in a chemical formula, what we're going to do is we're going to use parentheses around the polyatomic ions if we need to say that we have more than one of it in our formula. So, and again, we can use our cross-charge method to help us figure this out. Let's use a different example over here, just to illustrate this point. So let's say I have magnesium, and I'm going to combine that with an ion known as hydroxide. Okay, so magnesium we know is Mg with a 2 plus. And now we're going to tell you the hydroxide ion is actually a polyatomic. There are two atoms, O1 and H, and this has an overall charge of -1. So when I combine these, I'm going to combine them in the same way. Cation goes first, anion goes second. When you notice that you have a polyatomic ion, what you want to do when you start putting the formula together is go ahead and put it in a pair of parentheses like so. And then we can do our cross charge. So the charge on the anion becomes a subscript on the cation, so it goes there. And then the charge now on the cation, the 2, becomes a subscript on the anion, and the reason why we put the polyatomic is that that 2 now has to go on the outside, like so. So when we clean this up, this becomes MgOH twice. And we would name this as, just like we would, cation goes first, so the magnesium, and then the OH there is just hydroxide. So magnesium hydroxide. We don't change the ending of the polyatomic ion. We name it as it is. Okay. So that's how we are going to treat our polyatomic ions in our chemical formulas. We don't mess with the subscripts if there is already a subscript in the polyatomic ion. So for example, if you notice here, we have calcium and we have phosphate. Okay, so the phosphate ion here is already has the PO4, okay, in its formula. So when we put it in the compound, we keep the PO4 together in the parentheses. And if we do a cross charge, right, the 2 here becomes a subscript now on the outside of the parentheses, and the 3 here becomes a subscript on the calcium. Okay, we can confirm that the charges are going to cancel out. So what are these polyatomic ions and how many of them are there? Well, there are a ton of them that you're going to see. Some are going to be more common than others. Okay, your book, table 5.10, I think this here kind of splits it up. There's an error in this one. There are very few polyatomic cations, so positively charged ones, there are only 3 of them. There's the ammonium, there's the hydronium, and then there's the mercury 1, right? Out of these 3, ammonium and hydronium, these are the most common. So you need to know these. There are way more polyatomic anions than there are cations. So out of these, let's list the ones that you need to know. Now, I said there was an error here. The azide is not NH3. It is actually N3 with a minus charge. That's azide. We don't see that one as often. That's not one that you need to memorize, but I just wanted to clarify that as an error in this slide. Okay, so out of the polyatomic anions, we need to know acetate, which is this. Sometimes this is also written as CH3, COO with a minus charge. It means the same thing. This is more indicative of how the atoms are connected. Carbonate, we need to know carbonate. CO3 with a 2 minus charge. And we'll jump down here. Carbonate's friend, hydrogen carbonate, HCO3 with a minus charge, also known as bicarbonate, right? So you may have heard of sodium bicarbonate, right? Baking soda. It has that ion in it. Some other ones. We have cyanide that we need to know. We have, let's see, let me jump down here, and we'll come back to some of the others on top. Hydroxide, OH minus, which you talked about. Um, we have nitrate, NO3 with a minus charge. We have nitrite, NO2 with a minus charge. We have phosphate, PO4 with a -3. We have phosphite, PO3 with a -3. We have sulfate, SO4 with a 2 minus. We have sulfite, SO3 with a 2 minus. Okay, so you might see that there's a trend in some of these polyatomic ions. So for example, if we go between the eights and the ites, if I compare sulfate and sulfite, we will see that the only difference between them is the number of oxygens. Okay, the charge is the same for both. That's the same situation for phosphate and phosphite, right? The number of oxygens is different, but the charge is the same. For both of these, same thing with the nitrates and the nitrites. Number of oxygens is different, but the charge is the same for both of these. So yes, there are things you need to memorize, but we can minimize the amount of memorization involved. If you looked up here as well, we have chlorate and chlorite, right? Chlorate ClO3 minus, chlorite ClO2 with a minus charge. And what we also notice then is this can be taken one step further. Okay, we have where we hypochlorite, this one here, which has a ClO with a minus charge, and then we have perchlorate, which is ClO4 with a minus charge. So if we take those out and we list them right next to each other, we'll see that there is that same relationship, right? So our chlorate, ClO3 with a minus charge. We have chlorite, which has one fewer oxygen, so ClO2, but the charge is still the same. If we keep taking away an oxygen from chlorite, we end up with hypochlorite, which is ClO with a minus charge. If we take the chlorate, we add one more oxygen, we have hyperchlorite. Oh, I'm sorry, hyperchlorate. My apologies. We have perchlorate, which is ClO4 with a minus charge, right? So we see the same trend, the H versus the ites, one fewer oxygen. We take it one step further, we have hypochlorite, take one more oxygen away. On the other side of this, if we add an oxygen to the chlorate, we have perchlorate, so it's ClO4 with a minus charge. Okay, so the ones that I'm highlighting in yellow are the ones that are very common, and we need to know these. I'm going to highlight the chromate. We have the dichromate. What else? We have our oxalate ion, C2O4, 2 minus, and we have permanganate, MnO4 minus. It the 2 minus. So there are several of these that you need to know. Now, if you've taken any other chemistry class with us at OSU OKC, we did talk about polyatomic ions, and the list that you needed to know in those introductory classes was a smaller list of polyatomics. Well, now you're going further into chemistry, you need to know a few more of these polyatomic ions. Same thing if you would have seen this back in high school, right? You may have seen a few of these before. Now you need to commit more of these to memory because you're going to see a lot more of them. Okay, and we're gonna do the naming the same way like we would in the previous examples. If we have transition metals in there, we need to incorporate our Roman numerals in the names if we need to. So I mentioned, the nitrates, nitrites, chlorates, chlorites, etc. You will notice that what's common to all of these that we talked about were the ones that they have oxygens in them. So those are known as oxo anions that have, they are polyatomic ions that have one or more oxygen atoms. And then another atom, a central atom, that's a different element. And we see the relationship between them, the eights and the ites, for example. Eights have one more oxygen than the ites that have one less oxygen. Those oxo anions can become oxo acids, just like we've seen previously with the acids we talked about above. What's similar between the oxo acids and the ones we saw before is that these are also going to produce hydrogen ions. And then how we name them is going to be similar as well. So for example, if the name for the acid is going to be based on the polyatomic ion that is present. Okay, so the name for the oxo acids depend on, so the names for the oxo acids depend on the polyatomic ion present. So if the polyatomic ion was an 8 ion, then we would call the corresponding acid, an ic acid. So for example, the HClO3, okay, has the chlorate ion. So we would drop the ending here, replace it with ic. So this becomes chloric acid. If the acid was based on an ite ion, so for example, if I have HClO2, right, then you have to recognize the chlorite ion. Okay, so then this would become, drop the ending here, this becomes chlorus acid. And if we had, so for example, now we have HClO4. Okay, now we can recognize the perchlorate ion. Well, we saw the 8 ion above, so we drop the ending, replace it with ic acid, so this becomes perchloric acid. Okay, so we keep the prefix here in the name for the acid as well. All right, so another example, let's say we have HNO3. Okay, this has the nitrate ion in it. So just like with the 8s up here, this is going to change the ending now to ic acid. So this becomes nitric acid. Okay, if I have H2, SO4, okay, this has the sulfate ion in it. So this then would become, you may be tempted to say sulfic acid, but this actually becomes sulfuric acid in the name. And those are two very common acids we will see. So your oxo acids, we've seen how to name them. They can be monoprotic. Okay, monoprotic meaning that there's mono there meaning one. So one H plus one ionizable hydrogen can be lost. Or they can be polyprotic, meaning there's more than one hydrogen ion that can be lost. Okay, so phosphoric acid, for example, H3PO4 has actually 3 of these. So 3 H pluses that can be lost. And you can tell that from the formula of the acid itself. So for instance, the chloric acid, chlorous acid, perchloric acid, all of these are monoprotic because there's just one ionizable proton. Same thing with nitric acid, one ionizable proton. In the case of sulfuric acid, there are two ionizable protons, so that would be polyprotic. Okay, our last layer of nomenclature is going to involve now another class or another category of compounds known as hydrates. Okay, and then the word hydrate kind of tells you a little bit about what it actually involves. So, for example, when you hydrate, right, you add water to something. So when you say you're hydrated, are you hydrated enough? Are you drinking enough water? Same thing here. A hydrate is a compound that is going to have a specific number of water molecules within its solid structure. So water actually makes up part of the crystalline structure, and it's typically an ionic compound that has water molecules as part of its crystalline structure. Okay, so for example, the one that we have here that's written, right, just a little bit bigger, we have CuSO4, and then you see a dot 5H2O, right? So right away you think you're seeing something that looks very different. There's a dot in a chemical formula. How does that actually work? Well, that's the convention for hydrates. So we know how to name this part of it, right? So this is, we would name it according to the normal rules. So we have copper. Copper is a transition metal, so we need our Roman numerals. In this case, it's going to have a charge of +2 because now the sulfate here, sulfate is always -2, so the copper has to be +2. That's where the Roman numeral comes in. So copper 2 sulfate. And now the way that we rename the hydrate part of it, okay, we name it with the word hydrate at the end, and then we say how many of those water molecules are in the formula. Well, there's 5. Prefix for 5 is pentahydrate. So now we actually incorporate prefixes in the names. So this is where it gets a little, it might be a little confusing because we said it before. We only use prefixes for covalent compounds. Well, now we're actually using it for an ionic compound because this ionic compound is a hydrate. And we have to say exactly how many water molecules make up the crystalline structure, right? So this would be copper 2 sulfate pentahydrate. That's the full name for this compound. If we take a look at another example, we may have, let's take a look at this one here. Well, let's take a look at the one underneath because it's a different ion. So this now, okay, we can name the first part of it. So we have SR NO3 twice dot 4 H2O. Okay, so the first part here, we name it as we normally would. SR is strontium. Strontium is a group 2 metal, so we don't need Roman numerals in the name. NO3 is the nitrate ion, so this is strontium nitrate. Then the second part of the name, where the hydrate comes in, and again, you can tell it's a hydrate because you're going to see that dot in the formula. Okay, we're going to have hydrate as the last name of this. How many hydrates, how many waters do we have? We have 4, prefix for 4. Now we have tetra as our prefix. Our name there would be strontium nitrate tetrahydrate. So when we have these hydrates, because water makes up part of the crystalline structure, we can actually get rid of the water by just simply heating them. So for example, this here, okay, this is one of the things you talked about before. This is the copper 2 sulfate pentahydrate. That's blue in color. It's this thing. If we were to heat it, we can actually drive off the H2Os, drive off the water. And when you drive off the water and you end up with something without water at the end, well, guess what happens? The 5H2O go into the air, they leave. We end up with now just the copper sulfate, right? So we say that thing that we end up with that has lost the water, we call it anhydrous, meaning anhydrous literally means without water. Okay, so what you can deduce from this is that the presence of the water molecules actually imparts that blue color to the compound, right? And there are lots of hydrates that are used in a whole host of places. So for example, if you think about Epsom salt, that is actually a hydrate. That's magnesium sulfate heptahydrate, and Epsom salt, as you probably know, is used in a whole host of applications, right? That's just one example of a hydrate. There are some other examples of both um, uh, regular ionic compounds and covalent compounds that are used in a variety of places, right? We talked about baking soda. This is not a hydrate, obviously, which is sodium bicarbonate or sodium hydrogen carbonate, used in a variety of applications, cooking, etc. Milk of magnesia is simply magnesium hydroxide, right? Used for upset stomachs. Calcium carbonate, this one here, that is what you find in marble and chalk and limestone and even in your Tums antacids. Sodium chloride we talked about before. Ammonia, NH3, the common name for nitrogen trihydride, is used in, this is not the correct name for this, it's listed differently. And then we have nitrous oxide or a laughing gas, which common name is dinitrogen monoxide, used in anesthesia. So we see, both our covalent compounds, our ionic compounds used in a whole variety of places. Hopefully now, when you see some of these names on the labels of different things that you eat and drink or use, you now actually know what they're made up of.